Welcome back. In this follow-up video, we're going to talk about the limit definition of a directional derivative at a point a, b in the direction of a unit vector u. This is a follow-up from our introduction, and we'll go through all 5 steps of the process of constructing derivatives in this video. In order to construct a directional derivative, we're going to need some tools. The first thing we need is a multivariable function. In this case, we're going to assume it's going to be 2 variable input and a single variable output. We'll assume that it's a differentiable function, so we can take derivatives both in respect to x and with respect to y. Both partials exist. We'll also define a point on the surface of this function. So we're going to graph it and then choose a fixed point on the surface given by a, comma, b, comma, output point f of a, b. Finally, as we stated last time, we're going to define a general direction u given by a vector u1 and u2. And this direction is going to be a unit vector in the xy plane. So this is going to be a vector in the domain space of our function. Remember that the whole idea of the directional derivative was to construct a tangent line to the surface, z equals f of xy, at the point on the surface a, comma, b, comma, f of ab, where our limiting path was given by a general direction defined by the unit vector. As always, to create the slope of a tangent line, to create a derivative, we're going to use a 5-step program to salvation. Okay, remember always, 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 the 5-step program to salvation, aka how to construct a derivative. Step 1 is to graph a particular curve, C, we'll call it. Step 2 is to find 2 points on the curve, and then we draw a secant line through these points. Step 3 was to measure the slope of the secant line. Step 4 was to transform the secant line into a tangent line using a limiting process. And then step 5 was to construct the derivative of the function at the point as the slope of the tangent line, which comes from taking the limit of the measured secant line slope. Let's go ahead and run through these 5 steps for the idea of a directional derivative. To start with, we're going to think about how to construct a curve along a particular path. Remember that in the directional derivative, we don't want to move along the x direction or y direction. Instead, we want to go through the point a, b, and we want to do it in the direction defined by vector u1, u2. So this is a unit vector. Here, we'll call that line L of h. So this is a vector valued function. The input is a single parameter h, and the output is a multivariable vector. And notice that we're going to use the parameter h rather than t, and this relates to the algebraic convenience that we saw in the directional derivatives, that h is the distance of the run in the derivative calculation. Okay, we can use our understanding of vector addition and scalar multiplication to say that, oh, indeed, when we define our path in the domain, we have a parameterized linear curve where the x of h function is a plus hu1 and the y of h function is b plus hu2. And then we can draw this line in R2 as such. So the line L of h is a vector valued function. Here we're visualizing this vector value function in the domain. Notice that each point on this line as drawn is in R2. This is quite subtle, and we're going to refer back to this. When we look at the 2 points that we're going to use to construct a secant line, the first point is the point at which we want to measure the tangent slope, the slope of the tangent line, and we'll call that P naught of AB. This P naught is in R2. The second is a general point along this line L of h, and we'll call it P of A plus HU1, B plus HU2. So this is the second point. So we've just drawn this in the domain space. Again, we can say that this line in R2 in the domain is given as a parameterized set of coordinates, x of h, y of h, as seen above. And then we can also relate this back to the vector equation of a line where we're going through a point, constructed as a vector, plus any scalar combination of u. And remember, this is now the direction of u, since the direction in Math 1C is defined to be the set of all scalar multiples times a vector. So this is the line through point P naught in the direction of u. Here's where things get fun, and I know what you're going to say. They've been fun the whole time, and I agree they have. I'm right with you. Once we think about moving in the line L of h in the domain, we can project that line onto the surface to create a curve. So to trace a curve C along the surface. And I want to use trace kind of liberally. This is not a traditional trace that we spoke about in lesson, I suppose it was lesson 7, I suppose? Or maybe it was lesson 5, I forget. It's not a trace by intersecting a plane in the direction of x or the direction of y or direction of z. Instead, it is the intersection of a very, very special plane with the surface, and that intersection is a kind of a some sort of curve in R3, where the output points of this curve are given by the function z of f of xy, where we limit x and y to be on the line L of h. So the output points of this curve are z of h is f of L of h. And again, since this is a vector valued function, really this splits into two coordinates, which is good because f is a multivariable function. So you expect two inputs. And then again, we saw on the last page of this video that h of x of h was given by this linear equation and y of h was given by this linear equation. And then what's really cool about this is when we think about what the curve is going to be the set of all output points where the input is limited to x of h, y of h, and then the output is given by f of x of h, y of h. And then the only thing is that we let our parameter be in some interval around the point A, B. So in this case, we probably wanted to go like, I don't know, negative epsilon sugar. So maybe you say that our interval is like, I don't know, negative epsilon. Yeah, where our interval for our parameter includes the point A, B, where 0 is an element of I. And notice that x of 0 is A, because if you just put 0 here, those cancel out and I have this. Y of 0 is B, and then z of 0 is f of AB. And so in general, you might say that your interval is centered around 0, and maybe you go epsilon in the negative direction and epsilon in the positive direction, where epsilon is chosen appropriately for the limit. Hint, hint, hint. But anyways, you have this curve along your surface. Let's visualize this curve, which is the step 1 of the process of constructing derivatives. So here we have this curve C, which has 3 coordinates, x of h, y of x, z of h, where our parameter h is chosen appropriately. We can graph this curve as the intersection of the plane through the point P naught on our surface, and then with the normal vector orthogonal to the direction u. So remember that the direction u was in the domain space, and it was u1, u2. To construct a plane, we need an orthogonal vector. So if you were to just swap the coordinates of that unit vector, put a negative on one of them, I get the normal vector. So if I take these two dotted with u, I get 0. And since the plane is in R3, I need a third coordinate. So I say my normal vector is now negative u2, u1, 0. And then to create the curve, we're going to intersect this plane with the surface. Let's go ahead and visualize this. Okay, so here we go. Here, this thing, perhaps you call this surface, I drew this in Mathematica, and we'll actually do this in the next example for a particular surface. So let's say that this is f of x, y is equal to z. There's some surface. We have a line L of h, and you got to be careful. This is a different line than the previous L of h because this line is visualized in R3. It happens to have the same x and y coordinates, but the z coordinate is 0. So this is the line in R3 that comes from adding a third coordinate onto the one that we saw in R2. And then we have some plane defined by this line. And again, the plane is defined by a normal vector and then a point. So here's the point that we're going to graph through. Oh, I guess in this case, I actually said that the point was point A. Sorry about that. Point A is the one on the surface. Point P naught would be the one in the XY plane. Okay, so here, that yellow thing right here is the plane. We intersect this plane with the surface, and that intersection is a single curve. So we'll call that curve C. And notice, if we look at this curve as being in the plane, we can then choose 2 points on that surface by projecting the domain space points onto the surface. So the plane contains the points P naught, A, B, 0, and P of A plus HU1, B plus HU2, 0. These 2 points are in R3, and when we project those up, we get the images of those onto the surface, and then the curve connects those images. This is quite beautiful because it allows us to say, hey, we have now constructed a single curve upon which we're going to place some points to find a secant line. Okay, let's go on to step 2. So in step 2, we're going to find 2 points on this surface. The first point is going to be the one that we wanted to begin with, which was just to set the parameter h equal to 0. So we'll call that point A. We'll call it x of 0, y of 0, z of 0, which of course works out to be the point A with coordinates a, b, f of a, b. Point B comes from moving h units along the vector u. So let h be some general parameter value that's not 0. Move along the vector u, and you'd get this point B, which comes from a plus hu1, b plus hu2, and then the output value of the surface evaluated at h. And of course, this happens at f of a plus hu1, b plus hu2. Let's go ahead and visualize this. Okay, so we had this idea. Here's the surface. We intersect that surface with a well-chosen plane. Here we have the curve in red, which is the thing that we're going to try to find the tangent line to. To begin with, we construct a secant line through these 2 points. Well, we've just constructed the exact coordinates of those points. So when we connect those with a line, we've drawn the secant line that we were looking for to begin with. So that secant line is highlighted in blue, and we've just finished step 2 of our process to salvation. Yay! A little bit harder than what we did in partial derivatives because it's a different direction. Let's go ahead and visualize this line as if it was in the plane. So we're going to take the view along the normal vector. So we're literally looking directly perpendicular to that plane. So we had this curve C. We had the blue line through this curve C, which was the secant line. And then we said that the slope of this line is going to be the rise over the run. So here I'm evaluating f at the input point P naught. Notice, both of these points are graphed as if they're in the domain. As you're watching this video and making your own notes, make sure you're very, very careful about when you're visualizing stuff in R2 and when you're visualizing stuff in R3. Anytime you're looking at points along a surface, this P naught is in R3, this line is in R3, this point is in R3. here, the moment that we're looking at input-output relationships, because the input of this function is in R2, these points by definition must be in R2. Okay, so here this was the point A, this was the point B, and what we wanted to do was to find the slope of the secant line, which we would call M of AB. Well, we know this is going to be the rise over the run. Well, let's take a look. What's the rise? Well, the rise would be f of p minus f of p naught. What's the run? Well, the run would be the length of this vector. It would be the length of the vector connecting p naught to p. So why don't we just call that length the length of the vector connecting p naught to p, which we'll use a 2 norm to measure. We're not done because we actually can evaluate exactly what those should be. So this would be f of a plus hu1 b plus hu2 minus f of a b, and then all divided by the length of the vector that connects p naught to p, which we're going to write in 2 norm. Okay, so that's the slope of the secant line. However, you notice that the slope of the secant line has something in the denominator which is actually not as easy as the way that we did before. When we were looking at partial derivatives, because the vector u was in a pure direction, either 1, 0, or 0, 1, the length of this was just the value of the parameter h. However, here, because it's not a pure direction, we actually have to do a norm calculation. So in order to do this, I want to map back into the domain space. So we want to calculate the run to get the slope of the secant line. We're going to think about the run as the change in distance in the domain between our 2 points. To find the length of the vector p naught to p, we want to know how far do you have to travel from p naught to the point p in the domain. Well, here's a visual of this problem. We're looking for the length of this vector. So we want to find how long this vector is. And what I want to do is I want to kind of remind us how to do this length. Well, recall that the vector connecting p naught to p will have coordinates. We know that the vector p is given by a plus hu1, b plus hu2, and then we're going to subtract the coordinates of the point p naught, because that's how you could do these things. You take this one minus this one, and it gives you the coordinate of the vector connecting them. So here what you notice is that this is going to be a plus hu1 minus a, and this will be b plus hu2 minus b. And of course this is just h times u1, h times u2, which we can invert scalar, bring the scalar out via scalar multiple in reverse. Okay, and then now this is just h times the vector u. Okay, well, we just saw that when we wanted to take the norm, we could do this one of 2 ways. We could use the actual definition that comes from the Pythagorean theorem, or we can use algebraic properties. So this would be h times the vector u. I'm going to go ahead and use the algebraic properties. If it's not clear how I do this, I would encourage you to go back to videos in lesson 1 and 2 to see how I did this. So here I just brought out, and also I think it was lesson 3 perhaps, I forget. This is called homogeneity, where I factor out the h, and because I'm going to get a square, I could actually do this for you. So here this would be hu1 squared plus hu2 squared, and then I can factor out an h squared here. So this is going to be h squared outside of u1 squared plus u2 squared. And then, of course, this is the square root of h squared times the square root of u1 squared plus u2 squared. And that's exactly what we see. This is the norm of u, and this was the absolute value. But recall, we constructed this in such a way that this was a unit vector, which means that the length of this is just the absolute value, because this is a unit vector by construction, by assumption when we started. I wanted to make a very, very subtle point here. We're going to take, as we see, later we're going to take a limit as h goes to 0. This gives you the length of the piece connecting your two inputs, but it eliminates the direction at which you're approaching A. Because we're constructing this as a length, we're taking the absolute value. Really, when we start taking tangent lines, we can let h come from above or we can let h come from below. And we'll see this when we take the limit. We don't have to use the absolute value of this. Instead, we can just use h. Okay, so the whole idea is we've now got the run. So the slope of the secant line, what we just saw was m of AB was given by the difference between the run on the function, the rise of the function versus the run. And then this is where I'm going to do something crazy. This was f of A plus HU1 B plus HU2 minus f of A comma B. Here I'm going to actually completely violate this concept of run as length, and I'm going to think about instead the run of this thing is the amount of the vector u that we take, aka the scalar h. And what's really nice about this is h can be negative or positive, right? And we saw this when we took the slope of a tangent line. I can come from above or I can come from below. So if I came from above, this would be called, h going to 0 from the positive side. If I came from below, if my other point was below this, it would be h coming from to 0 from the negative. So this was kind of a loose definition because we were thinking about run as the length of a vector. This is the actual definition when we're prepping ourselves to take the slope of a tangent line. Okay, so we've just done the third step, which was to measure the slope of a secant line. The next thing we're going to do is to transform this secant line into the tangent line and construct the derivative in the exact limit that we want. So we said that in order to find the slope of a tangent line to the curve C at the point f of AB, we would take the limit. And in this case, we're going to say that the limit is with respect to the parameter h, and we'll say that this is exactly f of A plus HU1 B plus HU2 minus f of A comma B divided by h, right? And this derivative is actually called the directional derivative of the function f evaluated at the point AB in the direction of unit vector u. So that's how you read that notation, the directional derivative of f at AB in the direction of u, where this is now a unit vector. And again, if we actually thought about what this means, this would be the slope of the tangent line to the curve if we slapped a tangent line onto this red curve. And the way that we slap that tangent line on is we take a secant line and then we force P to P naught in the domain. In the next video, we'll actually construct an example using Mathematica to visualize this, and then we'll go on to talk about algebraic properties and how to apply this. This is an extremely deep derivation that has very, very powerful implications, which we're going to get into in the rest of this lesson. I encourage you to make sure you understand this derivation. It is the source of all knowledge for directional derivatives. Okay, in the next video, we'll go into an example using Mathematica. See you there.